record button. Okay. So what we have here is we've decided that this is 10 millivolts. 10 millivolts. I've got 1 k ohm. I've got, what was it? 13.2 ohms. And I've got another k ohm here. And what we want to find is we want to find this V out. So to use the voltage divider, I have to find the REQ of this parallel network. So REQ, and I can still get V out then because I haven't messed around with V out. REQ is 13.2 in parallel with 1K. Now somebody's asking a question. Yeah, in the AC model, the diodes are basically treat them like resistors. In the DC model, we treat them like a DC source or an open circuit. So that was the funny part. I said we had to derive from the DC circuit before, and I didn't explain that. If I want to find, and what does that come out to be? Of course, I didn't calculate it. If I want to find V out would be the plus or minus 10 millivolts on the input. This is the voltage divider, times the REQ, whatever that comes out to be, over REQ plus the 1K. And so this V out is, drum roll please, 130 microvolts when we do that calculation. So what I've done is I've taken, if you think of this as being a DC power supply with plus or minus 10 millivolts of noise on it, I've taken that DC power supply and turned it into a 2.1 volt supply with 130 microvolts of noise on it. So I basically built a bad voltage regulator. And the people at National, on semi, places like that, they actually build these voltage regulators in packages to perform this magic for you and give you really low noise output on the output. Most people just buy these. But knowing how they work is important too. You may have trouble with it. So
I'm sorry, but
yeah, go ahead.
Can we go back to slide 6? It might on the side there look like slide 5, but I didn't get all of the.
Okay, once I reboot my computer, I lose all my doodles. But yeah, they will be on the video.
Check the. Yeah.
Okay. Okay. If it's a specific question, I can help you with it. Okay. So the input voltage is the AC plus the DC part. This is the total voltage equals AC plus DC. It's kind of like superposition. And why am I not surprised? And that's on the input. The total output voltage equals the, and actually this is the DC part, the capital, the DC plus the AC. So what I've got here is there's my input voltage. My output voltage we decided was 2.1 plus or minus 130 microvolts. This is just a bad regulator, but it is a voltage regulator. And there's people whose life work is to perfect those regulators.
Sorry, but did you say that the voltage output equals the voltage total?
Yeah, the total voltage output equals the DC voltage output, which from like slide 7, we decided was 2.1 volts DC. And then on the last slide, we decided the AC part was plus or minus 130 microvolts. So I'm actually mixing units here. So the total voltage would be the sum of those two.
Okay, thanks.
Okay. All right. I never understood what that slide meant, but I just left it in there. Transfer knowledge from one thing to another or something like that. Okay, so now we're going to look at some circuits and how people use these. The biggest place I see them are ESD protection. We won't talk about today, but I will get to that much later. We use them for rectifiers to turn AC power into DC for power conversion. And we use them for limiters. There are some circuits in your cell phone that, let's say I've got a 3.3 volt supply going into the cell phone. There, oh, should I tell you? Somebody builds a PC printed circuit board in the lab. And there's different logic devices on this circuit board. One of them is a 1.2 volt logic chip. Most of them are 3.3 volt logic chips. And they decide to power this entire PCB board off of 3.3 volts. What happens? You plug it in and there's smoke and flames. And then there's a month delay in your project. Okay. You always check, because some of those like 1.2 volt logic devices are going to, if you look at the specification for them, they have an absolute maximum on the voltage, and that may be like 1.5 volts. And if you go above that, you're going to damage them. Now, the purpose of these limiter circuits are to limit the voltage to sensitive parts so that they can't be blown up. I can never get more than 1.5 volts or 1.2 volts to that part if I put a limiter in front of it. Or if I check the power supply ratings before I build the board and make sure I have 2 power supplies on there. Just put a step down regulator on the 3 volt 3 supply. That would have been a really easy fix. I wasn't there. So we want to plot a couple of lines. So the first ones we're going to plot is y equals 0. This is going to look silly, but I see people mix this up. So y equals 0, we're on the y-axis, and if y equals 0, what we have is basically the x-axis. I used to mix this up when I was an undergrad too. If I want to draw y equals 0.7, I go up here to 0.7 and I get a constant. So that is this one right here. If I want to draw y equals negative 0.7, I have to go on the negative axis, and this would be negative 0.7, and that would be right here. Now, the next thing I could do is I could do y equals x. So for y equals x, remember you get a line with a slope of 1 that passes through the origin. And there'll be a point to this that has to do with electronics in a minute. This is y equals x. That looks like a resistor. If I have something that, let's really change colors now. Green. If I have y equals x minus 0.7, well, if I'm at the y-intercept, if y equals 0, if x equals 0, let's do that one. If x equals 0, which is the y-intercept, then y equals negative 0.7. And I still have a slope of 1. So there is the line, this line right here. And I've got a third line, which I'm going to put in a different color, something completely different. Sparkle. Now let's do the bronze sparkle. Okay. And then we would put this one right here. It would have a y-intercept of positive 0.7 and still have that same slope, and that doesn't look all that different. So that would be this line right here. So we're going to be plotting lines like this. This is your introduction to something called the voltage transfer curve, the VTC, and we're going to be looking at some of these for some of these circuits. But then we go back and we're going to go back and look at some half-wave rectifiers first. I don't understand the order of these slides anymore. Remember, diodes conduct current much better. This is kind of a review of current much better in one direction from the other. If I have an AC input, like right here, and I run it through a diode, it's going to cut off all the parts of the curve where the AC input's less than 0.7 and just give you the top half of the sinusoid. This is something that has a DC component, and we can filter it and run it into a regulator and make a nice DC signal out of it. If during the negative half of the cycle, right here, the input voltage is always less than 0.7 of a volt. So during the negative half of the cycle, I'm going to have an open circuit here. This is where the DC model kicks in. This becomes an open circuit. This is just a battery, plus, minus. And if it's an open circuit, then the voltage on the output's always going to be 0. So my total curve is the positive half cycle plus the negative half cycle. So we could actually plot what's going on. We get to do this in the lab, in lab 5, and we'll do it when we get to the limiters and the rectifiers. This is a rectifier. It's a half-wave rectifier. And we call it a half-wave rectifier because only half of the wave actually gets signaled to the output. Now, if I want a full-wave rectifier, I could use something like that diode ring that we looked at last class, which is probably the most common way people do it. Or we did this in the 188 lab, or we used to do this in the 188 lab. Is we took an input voltage and we ran it into this center tap transformer. And basically what the magic of the center tap transformer is, I get a smaller version of this, my input signal over here. And over here, I get a smaller version of the signal, but it's phase shifted by 180 degrees. Which is like the same thing as multiplying a signal by -1. So during the positive part of the cycle, during this part of the cycle, this voltage is positive and this diode turns on. So this is from the positive part. During the negative part of the cycle, what happens is I get the negative of this voltage here. So this is the negative part of the cycle, is what that signal looks like. When I run that through the diode, I rectify it and I get the second half of the signal. So it's flipping the polarity of the negative half of the signal up to positive, which gives me more power than if I just half-wave rectified it and threw half the power away. So it's a lot more efficient to do a full-wave rectifier, energy efficient to do a full-wave rectifier. And if you want real energy efficiency, you go to switching circuits and PWM, and Dr. Yermasu will talk about those a lot in his classes. And I've taught that class before, so they thought my first senior elective. So this is the whole idea behind a DC power supply. And thank goodness I took these, and this used to be a matching problem and it drove me batty. I put them in order here. I've got the AC line voltage is a large voltage. It goes into the transformer and it becomes a smaller voltage. It's still AC, same frequency, same phase. And then I run it into, this looks like a full wave rectifier. And the full wave rectifier is going to take the negative half of the signals and flip it over and lose a little bit of voltage across it. Then I run it through a filter, and the filter, like I showed you yesterday, is usually just a big capacitor. It's generally a polarized capacitor that stores the charge when the signal's high, and then releases charge when the signal's low to help maintain that voltage. So that capacitor does a pretty good job of turning it into DC. But for sensitive electronic circuits, their performance changes if you change the supply voltage by too much. So the next thing is to go out and buy a voltage regulator or design a voltage regulator and turn this rippley signal into a flat DC. Now, if you look at this signal right here, I want to talk about this a little bit because it shows up in the lab. What we have here is a signal that looks like this. And the way they quantify this signal from a circuit designer's perspective is there's a couple of things going on here. They will specify the peak-to-peak voltage on that, and they call that V ripple. And generally, they'll the power supply designer will be given a specification that you have to keep the ripple within 10 millivolts, within 1 millivolt. If you're dealing with numbers, just make it 0 microvolts or whatever it is. If you're trying to read a very sensitive circuit where you're only putting 100 nanoamps in it, then that ripple requirement gets smaller and smaller. You'll get to measure ripple in the lab, and that's what we're talking about. So this is the first part. All this does is the rectification and the AC. And why is that? Ooh, that's magic. Okay. It does this part. Okay. So, and it's a full wave rectifier, and that's what that piece does. This is also a, we just looked at this one. This is also a full wave rectifier, and again, all this is the transformer and the rectifier. The output looks like this. If we wanted to clean that up, we'd have to put a filter and a voltage regulator past it. Okay. Now, this is a voltage transfer curve. Let's look at this, and we'll see lots of these, especially in 380 and like all over the place. This is the input voltage right here. So the input voltage to the circuit, and this is my output voltage. So we're plotting the output voltage versus the input voltage. Now, in here, I've got something that looks like Y equals KX in this slopey region right here. Generally, for pretty much most of the circuits we look at, K equals 1. It has a gain of 1. So that's like K equals 1. The slope of that line would be 1. And I want to design a limiter circuit that the absolute maximum voltage I can put on this circuit to prevent it from blowing up is 3 volts. So what I'm going to do is I'm going to, if my input voltage exceeds 3 volts, I want my output voltage to stay constant at 3 volts. So if Vn is greater than 3 volts, my V out equals 3 volts. Now let's look at the next part before I do this again. Down here, I want to limit on the negative side to negative 2 volts. So there's my negative 2 volts. If Vn on the Vn axis is less than negative 2 volts, I want my V out to equal to negative 2 volts. And in between there, if Vn is greater than negative 2 volts and it's less than 3 volts, then V out equals V in. Pretty much what that circuit's doing. V out follows V in unless I hit these rails, and then it's going to saturate and stay right there. That's the goal of a limiter circuit. We just sketched the VTC. I just filled in the numbers on that one. Now, if I put a sine wave into this circuit, I want to just do this someplace else. Let's see what happens. I want more space. Oh yeah, I'm trying to explain project stuff to the seniors. We have these open-ended projects in my senior class where I just give them vague instructions on purpose, and then let them mess things up. It takes a lot more of my time because when they mess things up, I have to go in there and help them out, and I don't know what they've messed up. But it's fun. I think people learn more that way. So this one, it represents 5 cosine omega t. Cosine omega t. Now, if I put this in my limiter circuit, oh great, you're in the wrong place. And you're sorry. And okay, so that's fine. I put this in my limiter circuit. This is 5 volts. This is 3 volts. This is -5. And this is -2. If I put this into my limiter circuit, what's going to happen is V out equals V in until I get to 3 volts, and then it's going to limit. And then when I get back, my input gets back below 3 volts, it's going to follow V in until I get to -2 volts, and it's going to limit. And I go up here and it does the same thing. So it's lopping off the tops of those, and you probably saw that happen in the op-amp lab in 188, or the guy at the big bench next to you saw that. This is the easiest way to fix that, and all circuits do this. They limit at some voltage, sometimes not intentionally. But yeah, that's basically what you've got. It's a sloppy square wave, and no, that's not how you make a square wave generator.
You muted yourself by accident.
Now I unmuted myself. When I'm dragging that screen around, I tend to mute myself occasionally. Thank you. So the same thing we just plotted. If I'm plotting V versus I, V out versus V in, sorry, I could plot those same lines on here. This is V out equals 0 is the x-axis. V out equals 0.7 is up here. It's the same thing we just plotted, only with V's. So I'm not going to spend time on that because I want to get to my circuits. Oh, I put these in this morning. Let's see how good I do with this. Rectifiers versus limiter circuits. We've already talked about what a rectifier looks like. Basically, I've got some voltage source here. I put a diode in series with it, and I put a resistor across the load. Now, there's 2 conditions. Oh, it says, is there a note to myself on here that says don't do this? No, that's on the next slide. But I won't do that. So what I would get out of this circuit is if Vn, this is the Vn axis, if Vn is less than 0.7 of a volt, this diode is off. It's an open circuit, and we'll look at the, I'll do this in detail in a minute. And I get 0 volts out. If I get greater than 0.7 of a volt, V out's going to equal Vn minus 0.7. All I have to do to make a limiter, and this is the limiter version of it, is I swap the position of the diode and the resistor. Now, if my Vn gets to be greater than 0.7 of a volt, all the voltage is going to get dropped across the resistor, and the most voltage I can get across the diode is 0.7 of a volt. So that's going to have a VTC that looks like this. I think I got far ahead of myself on this slide without explaining things. So the explaining part is the next couple of slides. I just changed this resist Note to myself, don't plot yet. Resist the urge to plot. So we've got two different models here. So for the rectifier, it's going to take 0.7 of a volt to turn it on. So let's look at the rectifier first. So the rectifier, there's two cases here. If Vs is greater than 0.7 of a volt, then I have enough voltage to turn that diode on, the diode's on. And if the diode's on, then it looks like this. I just replace it with this. Now, a second condition is Vs could be less than 0.7 of a volt. And if that's true, the diode's off. And I would just replace the diode with an open circuit with its DC model. I can do the same thing with the limiter. The limiter, if I have a Vn right here, if the Vn is greater than 0.7, and this works for the limiter too. Let's limit our amount of stuff I have to write. If the Vn is greater than 0.7 of a volt, the diode's on and I replace it with a battery. If the Vn is less than 0.7 of a volt, the diode's off and I replace it with an open circuit. So that's the strategy we're going to use to figure out what's going on. We're putting AC signals on the input here. So sometimes they're greater than 0.7 of a volt and sometimes they're less than 0.7 of a volt. And it says, please don't plot these yet because I'm going to have more room to do it when I'm done here. So this is a rectifier. We're using the constant voltage drop model, and I'm probably not going to go beyond that this semester. We use the constant voltage drop model, so there's two possibilities. Vn is less, and I've said V, and these are the same thing. Vn is greater than 0.7 volts, my input voltage, then the diode's on, and I can redraw the circuit like this. That's not a rectifier. What was I thinking? That's a limiter. Plus, minus 0.7 volts. Okay, so this is Vn, this is V out. If I want to analyze that, then pretty much my V out is taken across a 0.7 of a volt source. So there's only one answer for V out in this case. V out has got to equal 0.7 volts. Now I've got another case. Vn, oh thank goodness. It's just not letting me draw. Okay, draw with touch, which is almost as annoying. Don't draw with touch, draw with my pens. If Vn is less than 0.7 of a volt, the diode's off. I'm going to replace it with an open circuit. So now I've got this. R, Vn, V out, reference to the same ground. And I've got an open circuit where the diode was. There's no path for current to flow. Current can't flow. There's no voltage drop across the resistor. So Vn equals V out. So if I want to look at this in the time domain, how this was going to work is I take my AC signal, looks like this, and it's 10 volts peak, so this is 10 volts. This is minus 10, and my key point here is when I get to 0.7. So my output, if VN, my gold line is greater than 0.7, V out equals 0.7. So everywhere up here, V out or VN equals greater than 0.7, V out will be pegged at 0.7. It will be limited to 0.7 volts. If VN's less than 0.7, VN equals V out. So I just follow the line. Yeah, you get to do this on the homework. It's called a limiter because it limits the maximum voltage to 0.7 volts. Now, if I wanted to limit the maximum voltage to 1.4 volts, I could use 2 diodes. If I want to limit the voltage to 5 volts, I could use a whole bunch of diodes or not do that. I could just do this. This is plus, minus. I could put a voltage source in series with it of 4.3 volts, and then it would limit it. 4.3 plus 0.7 will limit it to 5 volts. So a lot of things I can do with this circuit, and we'll do that in the lab. That's not the limit. That is a limiter, and this is a limiter. That's a limiter, and this is a limiter. Okay, so that's what we just did. This is another thing I could do with a limiter. I've got 2 diodes in parallel. So now I've got 3 cases on this one. I could have both diodes cannot be on at the same time. That would be logically impossible. I could have both diodes on. No, I can't. Both diodes off. Let's do, I don't want to do that one first, but I wrote it down. Both diodes off. I could have D1 on, and I could have D2 on. Now to turn D1 on, I would need, this is the plus, this is the minus, I need VN greater than 0.7. To turn D2 on, it's going in the opposite direction, so I need VN less than negative 0.7. And if it's in between those two, both diodes are off, so VN would be less than 0.7 and greater than negative 0.7. Okay. If D1 is on, I draw the circuit like this, R. D1 becomes a voltage source. And D2 is off, so it's an open circuit. My V out is 0.7. If D2 is on, my circuit looks like this. I've got a current, I've got D1 off. I've got, now D2 is pointing in the opposite direction. It's got its minus sign up, which means when I put the 0.7 of a volt thingy in here, voltage source, the minus sign goes up, and that's 0.7. So my V out in this case is negative 0.7. Negative 0.7. And in between, both diodes are off. I just lost my phone, which I can no longer log on to a computer without. I love NAUITS. Oh, never. Okay, never mind. In between there, I have both diodes off. And both diodes are off. So V out, VN V out equals V in. Now, if I really wanted to look at that fourth case where both diodes are on, what I would have is I'd have something like this. I'd have a plus 7/10 of a volt in parallel with a minus 7/10 of a volt. It's logically impossible. Things in parallel, their voltages have to equal, so that cannot happen. And if I want to draw what the curve looks like, the first thing I usually do, and I draw this much neater. My touch pad's where I'm resting my arm. There's my input, and there's neater versions of this in the slide solution. Minus 10, it's going to limit at 0.7 and minus 0.7, and of course I would have to label that as being in volts. Follows in between, limits at 0.7, and then that would be my curve. I didn't change colors, so what I'm going to do here is label this V out, and label this V in, and label this V out, and label this V in. So I've just basically limited the voltage between plus and minus 7/10 of a volt. Lab 5, week 2, what you get to do is build a limiter, and I give you to limit something like, I want you to build a limiter that limits the voltage to 4 volts and -2 volts. And everybody gets their own numbers. So it's basically a version of this, except you've got to put a voltage source in series with it. Be careful of the polarities. Okay. This is the idea behind, I want to limit it to, much time do I have? Oh, yay. Plus, minus. This is 5 volts. The way this symbol works is the long side is the plus and the short side is the minus. So these two, their plus signs are both on top, so they're going to add. This is going to limit at 5.7 volts because this will become a 7/10 of a volt source like this. And that's pretty much what that does. Let's talk about kind of what we do in Mar, because I want to just go through this. At least some of you will get it the first time. So I want to, let's say I want to limit at plus 4 volts and minus 2 volts. How would I do this? I put a diode like this, and I do this, and I would put a diode for the negative side, would look like this. It'd be going in the opposite direction, and I could put the voltage source going this way, and this way this would be minus, plus, plus, minus. Okay. Now, when we want to figure out what voltage that is going to limit it, this one is going to limit to, we'll call this V plus, to V plus plus 0.7 volts. So if I want to limit it to 4 volts, I'm going to put this at 3.3 volts because you're always going to have the drop on the diode. What you're going to find when you simulate this is it's not exactly 7/10 of a volt. Yours is going to come out to be probably around 0.6 or something like that. And so your voltage is going to be a little bit off. And you could tweak that source a little bit to get it to be exact. Or you could just say the reason why this is not exactly the same is because I didn't take into account the diode current when I approximated the voltage drop across the diode. Now this V minus source, this is a whole other thing. I just have to tell you. So this V minus source, if I want to limit that to -2, I would have, this is going to be V minus, and they're both going in the same direction. So it would be the negative, since negative's up, V minus plus 0.7. So I want to limit that to -2. I would make this 1.3. Now, really common mistake is what people do is they say, oh, this is a negative source. What I'm going to do is I'm going to make this negative 1.3 volts. Because now you've made it negative in the negative direction. You like double negated it. You've made it positive 1.3 volts. Okay, so don't do that. You can either put the minus sign up and draw it like this, or you can put the plus sign up and make it a negative 1.3 volt source. Either one of those means the same thing, but just don't negate it twice. And if you get through that part, this lab, that part of that whole lab is easy. So you're basically asked to design something like that. And I don't want to do this one because I see no purpose for this circuit, and I don't put it on the homework. So are there any questions on the homework or like the universe or anything? Yeah. Okay. Yeah. The phaser quiz. Uh-oh. Oh, okay. Eli the Iceman. That's all I remember. Okay. Let's see. I can call him up. I have that magic power. I just have to go here. Oh, this is going to require my cell phone. DB Learn. Watch this. I've only signed in on this computer 20 times today. Oh, it likes my computer still. Okay. This is 280. And yeah, the thing I went to today too, it was like, we've all been vaccinated. We're all still sitting 6 feet apart from each other, and we're all still wearing masks. But we were in the same room. Okay. This is, where is it? We're in here. So the phasers quiz, let's take a look at it. Pre-lecture quizzes, phasers. Oh, great. There's directions at the top. You should read those directions. And they will, okay. So in particular, is there one of these, any one of these? Okay, at the leading and the lagging. Oh, okay. Let's see if I can remember how to do this. It's been a while since I've taught 188. The phasers, okay, if you think about the phaser, the angle is increasing with time. So this real axis is, why is this default? Why is it not letting? Okay. The real axis is 0 degrees. Oh, it doesn't like that. The real axis is 0 degrees. And as time goes on, it's moving counterclockwise. And if you do that, this is counterclockwise this way. So if I look at this, which one is going to cross the real axis first as those two together move counterclockwise? And you're kind of looking at that acute angle. So the eye is going to be first. So the eye is leading. Okay. And you think about, and you always kind of think about the acute angle. If I put them, oh great. Let's do that. If I rotate these in time, and I can't draw on this.
Well, is it like if you're, I guess, rotating them and they're behaving the right-hand rule, but if you apply that, your thumb would be sticking outside of the page, not into it, kind of?
I've never heard that before. Okay.
Oh,
so
okay.
Let's take this, but that might work. That doesn't mean it's not right. IV. So I've got IV like this, and a little bit later in time, let's say, let's change colors. Because this is what I came across a lot in 188. Let's say a little bit later in time, these same phasers, maybe 180 degrees in phase later, are looking like this, I and V. they're still going to rotate in this direction, but I is always going to get where it's going before V is. You don't really have to think in terms of which one crosses the real axis first. It's whichever one's going to get where it's going the first. I is coming first, so I leads. Okay. Yeah, who knows who taught you 188 anymore? It's random. I'm sorry. We used to have people own that class, and I could yell at them, but now it changes from semester to semester. Okay, so let's go on. Let's see if there's any more. So let's go ask you guys this one. Which phasor is lagging in this case?
Would it be V?
Okay, I've heard several people say V, and that is correct. V's lagging. What is, do you guys, anybody have trouble with this one? Frequency and hertz. Okay, the way back in the day when we were like, we didn't have cursors on our oscilloscopes, what I would do if I wanted to measure, and we didn't have auto measure on our oscilloscopes either, I would pick, I can't draw on that, the peak values of the sine wave. Where's my, right here. What I would do is I go to my oscilloscope and I'd find what time this happens at, and I find the difference in time between those 2 points. So the difference in time, it's easier to measure peaks and zero crossings, so I would call that the period. So that is the period. So that I could measure off of there. And if I wanted to find the frequency is 1 over the period. And this is in seconds. And the unit here is going to be hertz. Now, if I wanted to find the radial frequency, that's the omega. And this is what kind of bites you in lab 4, part 2 and 3. Omega is 2 pi times the frequency. And that has units of radians per second. MATLAB likes plotting things in radians, radians per second. Multisim likes plotting things in hertz. And a lot of times if you like measure the frequency response or something like that, and you find you're off by about a factor of 6.2, either multiply or divide. It probably has something to do with this omega thing. And then let's see what else is in that quiz. Whatchamacallit, and this one, okay. The magnitude, oh great, of the cosine wave. I don't know what answer she's looking for. I didn't write this quiz. Oh, and I can't draw on this. The magnitude of that wave would be about, it looks like it's about 3 volts peak. If you want the answer in RMS, you take 3 and divide by the square root of 2. And that's just something you've got to learn. And it doesn't say magnitude in volts RMS or magnitude in volts. If somebody sends me an email, I will try it and check it. Well, in fact, I can try it and check it now. Where's my answer? Where's my answer choices? How do I put the answer in? What is the magnitude? Oh, I see it now. I'm going to put in 3. I'm going to put in 3. I'm going to assume that I need units, and that's the usual format. Now, in the time domain, which one is leading? Oh, great. This is the 0. Oh, great. I get back to you on this one. Which one's leading? Which one's going to... Okay. there's an answer to this. This is why I'm not a power person. Which one's leading? I want to say I, and I think it's because the peak comes first. And I'm going to try that, and I'll get it wrong. Save and submit. Which ones did I answer? 3 and 14 and 15. Okay, I don't care. I get as many views as I want. Oh, I can't do that. Did I get them right? Yeah, I got that one wrong. I got that one wrong too. Which one did I say was leading? I said the current was leading. Okay. I'm going to write this down on your sheet and I will send you guys an explanation. Question 14 on, I'll just send it to everyone, and 15 on phasers. I didn't write these quizzes, and my guess is that she's probably asking for the magnitude and RMS, or that I put units on it and I wasn't supposed to because I didn't read the directions for the quiz. And I can look at I can look up the answers and kind of like cheat on them. So I will explain that later. And it's been so long since I've done the leading and lagging thing. Ibrahim, are you here? Zach Price, Zach Schreiner, and Donovan.
I'm here.
Who is Donovan? Okay, so you are checked off. Got it.
Zach
What?
Price is here.
Zach Price is here. Okay. The only one I got is Ibrahim and Zach Schreiner. So let's go home. What?
I'm here.
Zach Schreiner's here also. Ibrahim's the only one missing. Okay.
I'm sorry, I didn't hear you, but I thought I heard you say that you were going to email the answers to us.
Yeah, I will.
For the extra quiz.
For question 14 and 15.
Oh.
Okay. Because people ask that question in class and it stumped the professor. This is why I don't teach 188 anymore. I did like power, and freshmen are a lot higher maintenance than you guys. Okay, so share.